Welcome to our exploration of atomic structure and electronic configuration. Today we'll journey from classical models to modern quantum mechanics. Understanding how electrons are arranged in atoms is fundamental to chemistry. We'll start with Bohr's revolutionary model and progress to quantum mechanical descriptions. This shows Niels Bohr, the Danish physicist who proposed the first successful model of atomic structure with electrons in fixed orbits around the nucleus. In 1913, Niels Bohr proposed that electrons orbit the nucleus in fixed energy levels, like planets around the Sun. Electrons occupy specific energy levels or shells, numbered 1, 2, 3, and so on from the nucleus outward. Electrons can jump between these levels by absorbing or emitting specific amounts of energy as photons. Each energy level can hold a maximum number of electrons, 2 in the first shell, 8 in the second, 18 in the third. This diagram illustrates Bohr's model with electrons moving in circular orbits at specific distances from the nucleus, each orbit representing a different energy level. Modern quantum mechanics describes electrons using 4 quantum numbers that specify their exact state in an atom. The principal quantum number n indicates the main energy level or shell, with values 1, 2, 3, and so on. The azimuthal quantum number L describes the orbital shape and ranges from 0 to nn-1. The magnetic quantum number m sub L specifies orbital orientation and ranges from -L to +L. The spin quantum number m sub s describes electron spin, either +1/2 or -1/2. Here we see the different orbital shapes: spherical s orbitals, dumbbell-shaped p orbitals, and more complex d and f orbitals, each corresponding to different L values. 3 fundamental rules govern how electrons fill atomic orbitals in ground-state atoms. The Aufbau principle states that electrons fill orbitals starting from the lowest energy level first. Pauli's exclusion principle says no 2 electrons can have identical quantum numbers, maximum 2 electrons per orbital with opposite spins. Hund's rule requires that electrons singly occupy orbitals of equal energy before pairing up. The energy order follows 1s, 2s, 2p, 3s, 3p, 4s, 3 days, 4p, and so on. This diagonal rule diagram shows the order in which atomic orbitals are filled, helping us write correct electron configurations. Let's examine specific examples of electron configurations and orbital diagrams for elements up to zinc. Hydrogen has 1 electron in the 1s orbital, written as 1s1. Carbon has 6 electrons with configuration 1s2, 2s2, 2p2. Iron has 26 electrons with configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. Zinc completes the 3-days subshell with configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 310. These orbital box diagrams show how electrons are distributed in orbitals for hydrogen, carbon, iron, and zinc, with arrows representing electron spins. Understanding electronic configuration helps predict chemical properties, bonding behavior, and periodic trends. Valence electrons in the outermost shell determine chemical bonding and reactivity. Electron configuration explains periodic table organization and element properties. Transition metals show variable oxidation states due to d-orbital electrons. Thanks for learning about atomic structure. Like and subscribe for more chemistry content, and remember that electrons are the key to understanding chemical behavior. This periodic table shows how electron configurations create the s, p, d, and f blocks, demonstrating the beautiful relationship between atomic structure and chemical periodicity.